Let's now consider the operator for a very important observable, namely the Hamiltonian. Now this operator and observable are very important because they are going to be tied deeply into our framework for building up, once we get out of discussing kinematics, for building up our framework for dynamics. And it should be clear that we need this for dynamics because the Hamiltonian is intimately connected with dynamics, and we know that through the de Broglie hypothesis because the value of the Hamiltonian is how we get the frequencies associated with the system. And frequencies, of course, are how a system changes in time. Now, there are various ways actually to get at operators. We can follow, of course, the very formal development that we were discussing previously in terms of a generic observable with these abstract transforms. Another way, though, is just to recognize you have your operator when actually, in fact, you get the proper averages using our general formula for averages. After all, that's how the operators get defined. And so if we think about just the average of the Hamiltonian operator, that's actually relatively straightforward for us to calculate because the Hamiltonian itself we know is the square of the momentum on twice the mass plus the potential energy. And we also know mathematically that regardless of any kind of crazy correlations, quantum or classical, the average of a sum is always equal to the sum of the averages. So this will equal the average of v of x, right? Plus then the average of p squared on 2m. But 1 over 2m is just a constant, so we can always just pull that out of any averages. So we really just have to figure out how to compute these two averages. And these start to look like things we should be able to deal with fairly conveniently. For example, if I wanted to know the average of the potential, I know I would bin my particles up at different locations, multiply by the number basically that land in each bin, and then multiply by the value of the potential that I'm averaging. So once again, this is just the standard statistical formula for computing an average. The probability is just psi star psi. So by now, we've done that manipulation enough times to know we can write it as a bracket. That gives me my psi star. And then I need to have v times psi, so I could write it as v of x times psi of x, if I want, or just v times psi. We know all these things are functions of x. So that gives me the first piece I need. The second piece, the square of the momentum, that's a little bit trickier, but I think we can see very quickly how that would occur. Once again, we have to integrate over all of our options. We would bin our different observations into different wave vectors k. So this will become p tilde of k. And then we want the momentum squared, so we don't want h bar k, we want h bar squared k squared, like so. And so the main difference between this and the previous momentum operator that we looked at is we need to get two factors of h bar k, not one factor of h bar k. And if we look at our logic here, the way we got h bar k is we multiply by h bar over I, and we took one derivative. So if I want to get two h bars and two k's, I would do that twice. I would be taking two derivatives, and I would have h bar squared over I squared, which is then just minus h bar squared times two derivatives. And then the rest will follow through much like above. I'll leave that somewhat as an exercise to the reader, but then this will become psi with, as we said, there's going to be a minus h bar squared, two derivatives with respect to x, acting on psi. And so then finally, if I combine this information, I realize the average of the Hamiltonian is going to be the sum of these two pieces with an extra 1 over 2m going in the p squared piece. So when I sum those two pieces, I'll have integral of psi star. Here, I'll write it out. Integral dx. That's what both of these inner products have, and they both have a psi star of x. And then it's multiplying different pieces. This first piece, p squared on 2m, gives me 1 over 2m times these pieces. So I would have minus h bar squared over 2m times two derivatives of x with respect to x of psi. Then I have to add on the part coming from the potential, which gives me a psi star. Then there's a v times psi in here, so there's v of x times psi. And we know then from our, we can write this as an inner product, right? This would be psi. And then I have this expression, h bar squared on 2m d squared x psi plus v of x multiplying psi. And we know, therefore, that this must represent the action of this Hamiltonian operator on my wave function. So that defines that operation. And therefore, if we want to write this as an operator, it says first do h bar squared over 2m times the second derivative of whatever function I'm operating on, and then add to that result the potential v of x multiplying that same wave function. So that then gives us our Hamiltonian operator, which then we can, of course, always use in calculating averages of our Hamiltonian in the standard way. Very good. So that covers then the basic construction of operators.